Welcome back to the deep dive. This is where we take the source material you send our way and really get into it.
Yep. Pull out the key insights, try and make sense of it all for you.
Help you get informed, quickly.
Cut through the noise.
Exactly. And today we're tackling something that, well, it can feel a bit overwhelming, honestly. Choosing the right CNC drilling machine
Yeah. So many options out there.
and getting it wrong. That can be a really expensive mistake.
Yeah.
We've got this document someone sent in. It lays out the really critical things you need to weigh up.
Right. So our job today is basically to unpack that, pull out the core ideas, the sort of practical stuff that can actually guide you.
Help you avoid stepping on those landmines.
Hopefully, yeah.
And this material, it makes a really strong point right at the start. It says, look, before you even glance at fancy features, bells, whistles, you absolutely have to get the basic physical capacity sorted. Like, can the machine actually hold your part? Is it stable?
Yeah, that's so fundamental. If the part doesn't fit or if it, shakes around when you start cutting.
Then nothing else matters. All the software, the speed, pointless.
It sounds almost too simple, doesn't it? But it's absolutely step one, getting that physical match right.
Okay, so let's dig into that first point the source makes. Workpiece dimensions and weight. Why is that table size, the travel range, the structural strength, why is that the absolute baseline?
Well, think about it. The machine has to physically hold and reach everything on your part. The material's pretty clear. If you pick a machine that's too small or, frankly, just not beefy enough for your typical jobs,
You're just asking for trouble.
constant trouble. The table obviously needs to be big enough for your largest parts comfortably. And then the travel, the X, Y, and Z movement. The spindle needs to be able to get to every single spot you need to drill.
And it's not just, does it fit?
Right.
The source talks specifically about structural integrity, load capacity.
Oh, absolutely critical. You put a heavy chunk of metal on a machine that's, well, kind of flimsy for that weight. It's going to flex.
It's going to flex. It's going to vibrate the second that drill makes contact. And vibration, it's the enemy of precision drilling.
Right. Where's accuracy finish?
Wears out your tools faster? Could even be a safety hazard. The machine has to be solid enough to clamp that part down and keep it completely still under the cutting forces. If there's deflection, vibration, forget accurate holes. Doesn't matter how good the program is.
Okay, so size stability, that's check number one. What's the next big hurdle this material brings up? It seems to move into the material you're actually drilling and how that affects the spindle and the power needed.
Yeah, this is about matching the machine's, let's call it muscle, to how tough the job is.
Yeah.
The source mentions, if you find you're constantly chewing through drill bits or the machine just sounds like it's really struggling.
Grinding away.
Exactly. You probably have a power mismatch. Drilling harder materials, things like high-strength steels, stainless, maybe some tool steels. That takes way more force, way more power than, say, drilling aluminum or plastic. Yeah. So how does that translate to the spindle specifically? What are we looking for?
You're looking at spindle power, horsepower, or kilowatts, but also, and this is crucial, torque. That twisting force.
You're right.
For those tough materials, or if you're drilling bigger holes, you need decent power just to keep the drill spinning smoothly. But you also need enough torque, often at the lower RPMs, to actually make the drill bite effectively.
Okay.
Without enough torque, the drill can sort of rub. Instead of cutting cleanly, it just generates heat, which is bad for the tool, bad for the hole.
So a machine that's great for zipping through aluminum with small drills might just stall out or damage itself trying to drill bigger holes in steel.
Precisely.
Yeah.
And the source material also reminds us, your cutting speeds, your feed rates, how deep you cut each pass, that all changes depending on the material.
Right.
And the machine has to be capable of delivering the right speeds and feeds effectively for the stuff you work with most. It's really about making sure the machine has the right kind of power, the right kind of force for the specific fight it's going to face.
Makes total sense. Material dictates the force. Okay, then the document gets into the holes themselves.
Yeah.
The type, diameter, depth. How do those details shape what you need from the machine?
Well, the holes you plan to make tell you a lot about the non-negotiables. Like the maximum drill diameter the machine can handle, that's a key spec.
Obvious, but critical.
Right. And small holes, they usually need high spindle speeds, very precise control. Bigger holes, they need that power we just talked about and that overall machine rigidity to handle the much higher cutting forces without vibrating.
And depth, you mentioned depth. That sounds like it adds another layer.
Oh, absolutely. Deep holes, and the source kind of defines that as, maybe deeper than 5 or 10 times the drill's diameter. They have their own set of problems.
Like what?
Well, first, you just need enough z-axis travel on the machine to physically reach that deep. But the big challenge is getting the chips out and keeping things cool way down there.
Right, chips packing up in the hole.
Exactly. So features like peck drilling, where the drill pulls back briefly to break the chip and clear it, become really important. And things like through spindle coolant.
Where the coolant goes through the drill bit.
Yeah, forces coolant right to the cutting edge. That's often considered the best way to flush chips out of really deep holes and stop the tool from overheating. But again, the machine structure itself has to be super stiff to keep that hole straight and accurate over that long distance.
Okay. And what about more than just drilling? The document lists things like reaming, boring, counterboring.
Hmm.
Do they need different machine capabilities?
They definitely do. Each one puts slightly different demands on the machine. Basic drilling is mostly about removing material fast, but if you need, say, a really precise diameter or a super smooth finish inside the hole,
You'd ream it or bore it.
you might move to reaming or boring. And boring, especially for larger holes where the tolerance is tight, that demands exceptional machine rigidity and really accurate spindle movement. The source puts it simply. Drilling needs power and chip removal. Reaming needs spindle accuracy, minimal wobble or runout. Boring needs that high structural stiffness. And deep holes need the Z-travel and good coolant or chip strategies.
So you need to think about the toughest hole you make regularly.
That's the key. Design for the hardest job.
Got it. Okay, so we've got size, power for the material, the whole geometry itself.
Yeah.
But what the quality, accuracy, and finish is the next thing the source hits on.
Right, and this loops back heavily to the machine's fundamental build quality. If you need holes positioned exactly right, or you need a specific mirror-like finish inside, the machine's inherent precision is critical. It's not really something you can just, add on later.
So how does the machine's construction deliver that quality? What are the key parts?
Well, the source correctly points again to structural rigidity.
Yeah.
A really heavy, well-designed base and column structure resist bending or vibrating under load.
Because any movement means the hole's off.
Exactly. Any flex directly impacts the hole's position, its roundness, its straightness.
Yeah.
Then you've got the internal components, high-quality bits like preloaded ball screws, precision linear guides for the axes. They ensure that when the control says move 10 millimeters, it moves exactly 10 millimeters with almost no play or backlash.
Super precise movements.
And the spindle itself, we mentioned runout before, that's how much the very tip of the tool wobbles as it spins. Too much runout and you get oversized, maybe slightly oval holes, definitely a poor finish.
Okay.
And of course, the source reminds us again, clamp the workpiece properly. Even the best machine can't hit the spot if the part itself is moving around.
Right. So achieving that high accuracy, that good finish, it's a combination of a fundamentally solid, precise machine, and then also using good technique, quality tools, the right coolant.
Exactly. The source really highlights that, your drill bit choice, your speeds and feeds, lubrication, they're all important, sure, but they can only work their best if the machine itself provides that stable, accurate platform to begin with.
Okay, makes sense. Let's shift gears slightly then. Speed, getting parts done. The document talks about production, volume, cycle times. If drilling is like the bottleneck in your shop, what machine features suddenly become way more important?
Yeah, if you're pushing out a lot of parts or you've got tight deadlines, then the machine's overall speed and efficiency really matter. The material points out a few things, like rapid traverse rates.
That's how fast it moves when it's not cutting.
Exactly. How quickly the axes zip around between holes. It sounds minor maybe, but on parts with lots and lots of holes.
All that travel time adds up.
Adds up significantly.
Wow.
Reduces that non-cutting time. Spindle performance also matters here. How fast can it spin up to speed, slow down between operations, shaving off seconds per cycle? And even the control software itself. Efficient drilling cycles, optimized paths, that can make a difference too.
And just keeping the machine running without stopping seems like a big factor for high volume.
Oh, definitely. If the operator has to keep hitting pause to clear out a bird's nest of chips,
You're losing time.
losing valuable production time. So, the source stresses good chip management systems, powerful coolant flow to wash chips away, maybe vacuum extraction for some materials, just keeping things clear so it can run continuously.
And for the really, really high volume stuff, the document mentions automation.
Yeah, that's sort of the next tier up. Automatic tool changers, total game changer if you use multiple drill sizes or need to countersink or ream after drilling.
Eliminates the manual swap time.
Saves huge amounts of time per part. And then for the absolute highest volumes, you start looking at things like robotic loading and unloading or pallet changing systems. That lets the machine run almost lights out, minimal operator needed.
Potentially 24/7.
Right. So when you're thinking about volume, the source basically says, consider how many holes per part, how complex the parts are, and how many finished pieces you need per shift. That helps you figure out if a standard machine cuts it or if you need something really geared for speed and automation.
Okay. So looking back at everything we've sort of pulled out of this source material today,
Mm-hmm.
it really drives home that point, doesn't it?
Yeah.
Choosing the right CNC drilling machine is definitely not one size fits all.
Not at all. It really truly comes down to deeply understanding your specific work. What are the physical parts like? What materials are you cutting? What kind of holes exactly do you need? And how good do they have to be? And how fast do you need to make them?
Those are the signposts.
They're the roadmap, yeah. The best machine for you is the one that lines up best with those unique needs.
And it feels like following that logical path, the material laid out,
Yeah.
start with the physical size and
Yeah.
the power for the material.
Fundamentals.
Then look at the whole details, the
Yeah.
quality you need, and then think about volume. That gives you a pretty solid way to approach it, doesn't it? Cuts through the confusion.
Yeah, it gives you a system, a way to evaluate machines based on what actually matters for your jobs instead of just getting, dazzled by a long feature list.
Right. Okay, so here's something to chew on, building on what we've covered from this deep dive today.
Hmm.
Given how critical those foundational things are, the physical size, the stability, the power for your materials, the demands of the specific holes you drill, how really locking down your absolute non-negotiables in those areas first stop you from getting sidetracked by maybe less important bells and whistles later on when you're looking at machines.
Hmm.
Maybe think about which single factor out of everything we discussed feels like the biggest potential bottleneck or challenge for the work you're doing right now or the work you're planning to do.
Yeah, something to really focus on right at the start of looking around. Good thought.